All right, let's get started today. I want to go through a little bit of the code that Professor Rim skipped because I think it's actually it's very illustrative, and the concepts that are there can be really nice to look at. But showing it in code and actually seeing what the code is doing is important for this. So I do want to take a little bit of a detour there. And then we're going to go through boundary value problems, a couple different ways to do that, and finish up the semester in terms of material. Again, I won't be here on Thursday, and Yvonne has actually graciously agreed to lead the final review discussion. The final review is posted. It is more indicative of the length of the exam this time. Well, indicative is an important word there. So if you have questions about that, the solutions will be posted after class, and the final exam will be available starting at midnight this Friday. So you'll have Friday, Saturday, Sunday, Monday to do it. So it's very similar to the midterm. It should be the same, we're shooting for the same length. It's going to cover mostly the last bit of the material we've done that didn't get covered in the midterm. It doesn't mean that we can't refer to things before the midterm, but that's the course coverage. Okay? So, yeah.
Is it going to cover material that was not in the homeworks, like the second half of the homeworks?
It's possible. I generally don't try to do that because you don't have any idea what I'd ask. So by and large, it'll be only from the stuff from the homeworks. I should also say I'm going to post the solution to the last homework as soon as I can, because there are still people who can turn it in late right now, which is why it won't be posted. But I'll try to do that immediately when I can. So probably sometime on Friday is my guess. Any other questions? Concerns? Feature requests? I don't know. Okay. So if you recall, we were talking a lot about iterative methods, and kind of the last bit of last Thursday was about really leveraging this kind of unique type of matrix that actually can be reformulated, or at least solving AX equals B can be reformulated as a minimization problem. So this is unique. It doesn't work for all matrices at all by any means, but it does actually end up being very useful for matrices that are coming from some type of discretization of a ODE or a PDE in space, which is why there's a lot of attention to it. So this particular cell kind of shows, at least in a 2D sense, what this minimization problem really looks like. So this is the plot of the contours of a function. Okay? We want to find the center, the minimization, because that's going to be the solution to the problem. That's kind of the idea here. So this is the identity. The identity matrix also satisfies this. It's a circle. You can go directly towards the center because there is no complexity in there. And then you can think of the complexity of the problem itself, or the difficulty of the problem, and actually the condition number of the problem gets worse and worse as you start stretching these ellipses. So the actual problem becomes more complex or difficult to solve numerically. So this is just a 2D example. You can imagine how complex this can be in 1,000 dimensions. So 1,000 by 1,000 matrix, you wanted to find the solution to AX equals B, you'd have an ellipsoid in 1,000 dimensions. So the dimensionality in this problem gets very, very complex, even though it has a simple minima. We don't have multiple minima. We don't have saddle points or anything like that. That's another problem, which you can actually use a lot of these methods for, but you do have to be careful. You don't want to get stuck in one of those local minima. So there's entire courses on optimization, and a lot of those optimization problems can actually be termed and used for these types of problems. Okay? So you will see conjugate gradient, you will see steepest descent, and you actually, one of the most popular ways to solve minimization problems today is stochastic gradient descent. And those work great for these problems as well. Although we don't need the stochastics, the kind of the randomness of those methods are because you have multiple minima, and you want to jump out of those local minima occasionally. So that's really kind of the connection to the broader world, especially of machine learning, to these types of things. But the theory that we're talking about here actually all applies to those methods as well. They're just a little bit more advanced. So if we can kind of continue on through our discussion here, steepest descent, you're really just looking at the gradient, the local gradient. You have a function, you can take the gradient of it, go in that direction a certain amount, tell you shouldn't go in that direction anymore. That is steepest descent. And you can solve our boundary value problem pretty easily that way. But the interesting thing here is that as I make my problem harder and harder, the identity, it solves in one step. That's a good thing. We would like to see that the identity is actually going to be solved in one step because it should be that easy. In the case where I'm making it a little bit harder, you can see there's a number of steps, and I'm pretty much around the minima here, and the iteration count is 8. But if I stretch those ellipses a little bit more, you can start to see the problem. Right, I'm going to go in the gradient direction, but the gradient direction might not actually tell me what's really going on. You can see that I get caught in this zigzaggy pattern, and I eventually get there, but the iteration count starts increasing quite a bit. Okay? So that's what conjugate gradient tries to solve. It says, can I actually do this a little bit smarter? Can I pick a better direction than the gradient to do this? And of course we can. So here, I think he showed you this picture. Instead of just picking the gradient descent, I want to pick something that's going to, in 2 dimensions, the basic idea is to just pick the direction directly to the center. Okay? So it's not the center of the ellipsoids in 1,000 dimensions. It's the center of the ellipsoids in a particular dimension. So I'm reducing the problem and solving it in a particular subspace of the total space, and I'm actually getting to the minimum in that space. So we can do that in the simpler spaces. And that's really the idea of conjugate gradient. I'm solving the problem in a reduced, smaller dimensional subspace of the total problem, which means that once I've done that for all the subspaces that exist that make up the real problem, I get to the solution. So dimensionality is really going to be the big constraint there. And sometimes that's actually even better because sometimes some of the dimensions don't matter that much. You can think like, well, okay, so this dimension, maybe the minimum is slightly off from what the real true minimum is. I can actually ignore that because I've reached my tolerance for my algorithm. So I can actually converge faster than the number of dimensions of my problem. So this works as well. It's a bit more complicated. You can see a lot of the complexity here. The biggest difference between steepest descent and conjugate gradient is the way we determine which direction to go. We kind of stick A inside of that dot product. So that gradient that we're calculating has an A stuck in it. And one way that this doesn't exactly work, but I like to think about it anyways, is that you're somehow transforming the vectors into the space that all the vectors that A is sending, so it's the column space of A. I'm actually computing in that space rather than the original space that I exist in. So somehow I'm taking the information from A, the fact that it's maybe making stretched ellipsoids, and I'm using that to calculate the direction I want to go into. Okay? So that's kind of the key observation here, and that's why we stick A inside of things, and you can see it's really A's right in there. So that would have been a dot product if not for A. So that's why we call it A conjugate. You were really just kind of sticking A in strange places. So we kind of negotiate that. So this is A conjugate direction. If it's equal to 0, that's just the dot product, if not for A. And that's really the idea that's coming here. And of course, if we actually look at the iteration count for the exact same problem, we see 0, 1, and 12 rather than 0, 8, and 67. So much quicker convergence. And you can see even for this problem, this is the initial guess. That's the first step. The second step is almost at the minimum already. So this is much better. We're choosing a slightly different direction. And that's really the key here. Like the gradient isn't a bad guess. Like that makes sense. You want to go in the gradient direction. However, we can actually guess better. It doesn't quite get to exactly what we want to see. Like we'd like to see this converge in 2 or 3 steps. And that's because there's some numerical error still going on in here. But you can see it does very, very well. It reduces the computation to only a couple steps. So that's kind of what I want to just go through. I'll just point out these particular points. Really, it's all about trying to take smarter steps in this type of problem. And again, there's a whole swath of different ways to look at solving eigenvalue problems even in AX equals B that use these types of ideas. You turn it into a minimization problem, a variational problem, and you solve it like that. You do need to have a special matrix to do that, but oftentimes in practice, that does actually be the case. You have some special matrix that does that for you. Okay. Any questions? And of course, we completely glossed over the preconditioning, which is incredibly important, but very specific to your particular problem, unfortunately. So if you have a particular problem, you're in a field, you want to solve a matrix, definitely look at your field's research, because I'm nearly certain there'll be someone who's thought of a preconditioner. The generic preconditioners can work, but they tend to be not as good as actually something specific, taking into account, for instance, the physics or the situation that you're in. And that's just because you're adding more knowledge to it. So a lot of these things act like that. Okay, so we will switch to boundary value problems. We've talked about boundary value problems a couple times. We motivated the last iterative section with boundary value problems, and now we're going to actually go through kind of more systematically, talking about their solution and different ways to handle them. So this is the basic problem. We've seen this before. We have some sort of spatial derivative. Uxx is equal to f of x, so this is the Poisson problem. So hopefully you've solved that before. It depends on what f of x is, of course, but you can integrate this thing if it's just this thing twice, and you get the solution. Oftentimes, you will write, partial derivatives. Maybe f of x isn't f of x. Maybe it's some function of u as well, so this problem can get kind of arbitrarily complicated for us. But we want to solve problems like this. These come up all the time and give us nice structures that we can leverage. So again, I want to emphasize the difference between boundary value problems and initial value problems. Boundary value problems dealing with space almost always. Initial value problems deal with time almost always. So there really isn't that much difference between the two, except that the fact that the boundary value problem has data at 2 different points in whatever independent variable it are, whereas the initial value problem really has data only 1 point. Okay, so if we have a second order problem, UTTs equals some function, that's an initial value problem only if we have data only at the initial time. Whereas a boundary value problem, the idea is that it has two different points in the independent variable. So the only reason I'm emphasizing this is because one of the techniques we're going to use is going to rely on this differential. And that's exactly what we're going to do. We're going to actually rephrase our boundary value problem in terms of an initial value problem and use everything we know from initial value problems to solve the ODE. The other way we've seen before, we use finite differences. We saw a system of equations, and basically what you've seen, and this is basically a lot of numerical analysis, is somehow you get a continuous problem into a discrete linear algebra problem, and you solve that. And that's the second kind of main technique to solve these types of problems. There are others that are much more specific, but this is fairly generic in this case. Okay, so the first method is called the shooting method. It is actually a searching method. The idea is that we're going to reformulate the problem from a boundary value problem to an initial value problem and guess what the missing data is, see if it works, and then check and come up with a new guess. Okay, so this is much better as a picture. If we have a problem where I know I have data at, say, two ends of an interval, a and b. So I know, say, u of a. I know u of b. That's a boundary value problem. If I add a ODE here, okay? What I'm going to do is I'm going to say, well, I have a second derivative, so I need two pieces of information to solve this problem, which I have, so that's fine. But the key here is that I'm going to say, well, I don't want to deal with b. I'm going to come up with something that says u prime at a, which I don't know, okay? But I'm going to search for that value. So now if I have two values over here on the left-hand side, I can solve this like an initial value problem. And what I'm going to do is I'm going to say, all right, so I'm going to solve this, guess what this is, and see if I hit this one, hence shooting method. Okay, so it's like you're shooting a cannon or something, I don't know. That's the basic idea. We don't know, we know what UB is, we know what B is, and I just want to make sure that I hit UB to some tolerance. So it turns into a searching type of thing. And I'm just going to use my initial value problem machinery to do that. And that's the basic idea. So let's go through a problem. So we have a problem, uxx is equal to negative sine u. Note that this is incredibly nonlinear. It is inside, we can't actually solve this. You can take the Taylor series and do all sorts of fancy things, but this is not a trivial ODE to solve. So we have some initial conditions, excuse me, not initial conditions. We have some boundary values, right? We have 0 and pi over 2 at 2. Okay. I'm going to reformulate the problem as two ODEs like we did for initial value problems. So we have a new variable v. The two unknowns are going to be u and ux. Taking the derivative with respect to x of these two things, it gives you ux and uxx. We know uxx is equal to negative sine v1, which is just u, and then ux is equal to v2. So exactly how we did this for initial value problems. So now I have to actually come up with an idea. So I can solve this once, but then I need to figure out how to actually make a new guess. So if I don't hit UB, how do I decide where to go? In this particular case, we're going to just minimize the difference between the pi over 2 and minus v1, 2. So this is just the boundary condition. So we're just saying we're going to minimize the distance between where I'm actually going to calculate the solution at 2 and the true value that I want to actually hit. And we can actually vary the parameter. In this case, it's actually easy. We can just use a bisection method or something like that. So stuff from root finding or zero finding to do this. Sometimes it gets a lot more complicated than that. So I don't think I opened this. So here's the idea. I'm going to give you a couple minutes to just think about implementing this. We'll implement this. We're just going to use SciPy's integrate functions. So feel free to copy that if you want. The biggest thing here is to try to figure out how to choose the next step and just see how it converges. This is unfortunately very hard to prove anything about, just due to the nature of the nonlinearities. But I do want to give you a few minutes to just think about what's going on before I actually end up just coding it up for you. There is a bunch of code here, though, so you know, don't get scared off from that. But we'll give you, say, 2 or 3 minutes, and then I'll code for you. Okay? Okay. So just to step through this code a little bit, we have some algorithm parameters. So we're going to say we need to be within this pi over 2, within 10 to the negative 8th. That's going to be our kind of the stopping criteria. We're only going to spend 100 iterations of this. So if we don't hit it by then, we will say we gave up. There's some problem statements, the domain, the space itself, the boundary conditions, and the right-hand side function. So that's kind of the beginning of this. We have an initial guess for the u prime right-hand side. So we're really, the true solution has some slope at that point, and we're guessing what it's going to be. And that's actually what we're searching for this. And then we also have an initial step size because we're going to be basically using bisection to do this. So we need to have some sort of interval that works. So again, both of these things are going to be problem dependent, and you're just going to have to figure out what makes sense and works. So we have the normal types of things. We have u, we have success, and we're going to just look at the convergence as we go. So the convergence is going to just be the difference between, in this case, the true boundary condition. So that's what we're counting as convergence in this case, and what we're computing the boundary condition to be. So we have initial conditions. We always have to set that because we are integrating. So we know one of them, the second one, is going to be our guess. So that's going to be updated. So this is just initial value problem, initial conditions, which is why we have 2. The second index is going to keep track of time or space, actually, in this case. Constructing the integrator, it's code we've seen before, so I'm just going to copy it. So this is what we saw from back when we were doing ODEs. This is how you do it for a scipy.integrate. So that's up here. We've imported it. And we're just looping through. We don't necessarily need to compute this many of them. We just want to see what's in between the endpoints to get the actual solution out, which is why we have an inner loop here. So next, we want to actually figure out, oops, that was not good. Come back, please. Ooh, okay. It's always exciting when the projector goes out. So really what we're going to do here, oh, actually, I already did that. At this point, so we've computed some solution. We know what it hit. So whatever it found as the right-hand point all the way up to 2, because that's the one place we wanted it to actually hit, we need to check it, right? So that's an if statement. We're going to actually record the convergence at this point. So we're just going to compute it as the absolute value of 0, and then last point we found, and the true boundary condition. So that's just what that's computing. And then we're going to check it. So if the difference between basically the same thing is less than our tolerance, then we're successful. So we're going to break out of the loop. Else we have to have another statement. We have to actually guess a new right-hand, like the prime, u prime part of it. The way we're going to do that is we're going to say if u0, -1 is less than ub, so that means we were too low. We're going to add du prime to it. So that means we're going to go up. So this is a bisection method here. Else we're going to go down. That's not what I wanted to do. And in this case, we're going to actually take and have du prime. So there's a little bit of a difference here from the bisection method. Bisection method usually would just always make it smaller. The nonlinearity here is actually a little bit trickier than that. We don't we have any of our bracketing that's going on here. We can't guarantee we have a nice function. So that's the one thing. We're only going to make our du prime smaller if we actually think we're below, or excuse me, above the true right-hand side. So that's really the kind of key to shooting method is somehow you need to figure out how to do this. You can have an initial guess and you can have a du prime, or somehow you have to come up with an initial guess and a new guess based on where you are relative to the true thing that you want. And that's completely problem dependent, unfortunately. This doesn't work too bad. Oops, let me do this. Okay, so we get something that looks like this. I should have labeled these, but so basically these are all our guesses. So we solved the ODE a bunch of different times. This is the true solution. So you can kind of see we're down here, jumping up, and we're closing in on that right-hand side, okay, just by searching to find the right guess for u prime at A, because we don't know that. Here's the convergence. So we're taking a number of steps. And you can see we're getting down to 10 to the negative eighth, but we're not doing well all the time. You know, this is a pretty jagged curve. We're not always making the right guess. So you can imagine there's lots of places where you could actually try to make this problem a little bit easier, or add more interesting examples of how to guess these things. But by and large, this does tend to work. You can, this is kind of almost a brute force type of method. If you know enough about your problem, you can do shooting method. It is expensive though, because you're solving an ODE problem, you know, above 60 times in this particular case. So just be aware that this is, although this is great, especially considering this is a nonlinear problem, it does have its challenges as well. Yeah, I just said that. So basically, you can use all your machinery from initial value problems, but you need to do a search algorithm as well. So that's an iterative scheme that you need to add to this. Any questions about that? All right. Linear systems. So this is changing the same boundary value problem into a linear system. We've seen a little bit of this before. Let's just go through it again. We have our boundary value problem, uxx equals f of x. It's going to be our standard. We have boundary values. We know that we can use the second order center difference to approximate uxx. So again, here's the thing we're going to use. So we're just evaluating u at various x points, discretizing the domain. We get some sort of discretization like this. So the xi's are going to be uniformly distributed. You don't have to make them uniform. It's just easier that way. So this is just saying exactly that. A to B uniformly distributed with n points. So notice that there's some trickiness with the number of points if you're including the boundaries of the domain, especially using linspace. Here's a 5-point. So we cut the domain up into 5 points that we don't know. So that would be, so if we're actually drawing it on our old picture. Oops. It'd look like this. So we're trying to solve the problem at x1, x2, x3, x4, x5. Okay, so not at A and B. We know what A and B is. We want to know the solution at x1, x2, x3, x4, x5. Using our approximation to the derivative, we can write that like this. And note that at the boundaries, because we know what UA and UB are evaluated at, we can actually add that into our derivative approximation as well. So we have an approximation. We have U1 through U5 as unknowns. We can formulate that as a matrix. That's what we've seen before. And then on the right-hand side of this matrix, we have the fx1 through fx5. So we're just simply evaluating f at those points. So now we have a linear system. We've seen this structure before, and we know how to solve this. Well, hopefully, at this point, we know how to solve this. Okay. So there's lots of different ways to handle boundary conditions. And this is where we're going to go into a little bit more depth. Here, we're kind of ignoring the boundary conditions. So if you look at this, this isn't actually taking into the boundary conditions at all. Right? We're actually missing what should be a 1 up here, and we're missing a 1 that should be down here, or cutting it off. And that's because we have this unknown vector, u1, u5, which doesn't include those. We need to have the right shape to this thing. So how do we handle that? Well, we know that this is the algebra for those 2 points. Right? We have ub and ua there. They're still there. We can just do a little bit of algebra on those 2 equations, stick them on the right-hand side, so that ua over delta x squared and ub over delta x squared is just on the b vector, so ax equals b. So I get this. So now this actually works. The only way the other one would work is if the boundary conditions were 0, which, of course, would mitigate that problem altogether. So we can actually just push the boundary conditions onto the right-hand side, and everything works. So this is taking into account the boundary conditions. It's a linear algebra problem. We see this matrix that we know how to solve, and we can go to town on this thing. All right, so we're going to do this again, because this is pretty fundamental to what we're trying to do. We can, of course, solve this problem. We can just integrate the right-hand side twice, so it gives us that solution. So we're going to construct this matrix. I'm going to show you a couple different ways actually to construct this, because like NumPy and SciPy actually do provide you a couple of ways to do this, which are interesting. Definitely you can do it with for loops. There are a little bit more efficient ways, and actually there's ways to do it in sparse matrix ways too. So I'll give you a couple of minutes to try to do this yourself. Copy your code. You've done this before in the homeworks. Try to set it up for this problem and see if you just using numpy.linearalgebra.solve can get this to work. And then I'll code up a couple of examples of how to do this. Okay? I'll give you a couple of minutes for that. All right, so I'm going to say that we all can do the for loop version of this. So we're going to construct it using just kind of intrinsics in NumPy, the first way here. So first of all, the main observation is that these matrices, I mean, and when it's n equals 10, it's not that big, but they're by and large zeros. There's not a lot of data in them. They're just, in this case, 3 diagonals. And we're going to exploit that in a little bit. But basically, starting out with zeros is a good thing to do. So that's going to be our basic A. I'm going to create a diagonal. Oops. Okay, so I'm just creating a vector that is going to be all ones divided by delta x squared. Because we know that the entire matrix is actually divided by delta x squared, so I'm just going to stick that in there right now. And the reason why I'm creating this diagonal is that one of the kind of easy ways to construct a matrix in NumPy is to actually use diagonal matrices or construct diagonals. So here I'm going to use the diag command, and I'm just adding it to A. So I'm creating a matrix that has a diagonal that's non-zero, and I'm adding it to A. Since A is all zeros, it's really just putting it into A. So this is going to, this command will take diagonal, multiply by -2. So that's the main diagonal of the matrix. And I'm putting it on the main diagonal. So that last argument to diag is going to say, I want this to be on the actual diagonal of the matrix. And I'm going to do this 2 more times. Putting the diagonal on the lower part. Oops. And the upper part. So the index is actually saying which diagonal up and down it's going to be. Now this doesn't exactly work. So the diagonal is going to be, this vector thing is n long. That's too long to put on the sub and super diagonals, right? Because the length of those are going to be reduced by 1. So in this particular command, you actually do have to take that into account. So we just cut off the last value of those diagonals. So that diagonal vector is going to be 1 less in length. So that gives us that. And our matrix A is actually done. There's all sorts of things we can do here. We can actually, something that's fun is to just say spy. Let's comment this out. I think this will work. Okay, so spy actually colors in a plot of where non-zeros lie in the matrix. So the indices here are actually the indices into the matrix, and you can see that it's just the diagonal values. So here you can see it's rather chunky because we're just using n equals 10, but I can actually make this big, and you can start to see some structure in the matrix. So this is a great way to debug, just to make sure that you have non-zero values where you think you have non-zero values. The other thing you can, of course, do is to just say, I want to print A if A is small enough. So let's actually go down to 5. So we have values there. Definitely, this is another debugging technique. The reason why these values are so big is because I'm dividing through by delta x squared still. So this is going to be -2 and 1. But you can see the structure should actually match what you expect. So again, another way to make sure that you're getting the right thing. I'm going to put this back up to 10. Okay, so we're not done yet. We need to construct the right-hand side vector. So this is f of x plus some other stuff. So I'm going to call it b just to be easy. B is going to be basically f. Right? I have f defined up here. So that's easy. If I have x, and it's just the interior points right now, because that's all I actually want to evaluate f at. And then I'm going to modify the endpoints of f so that they have my boundary conditions in them. Like that. So that's just basically taking into account these 2 points. And then we have our right-hand side. We now have an A and a B, and we just need to solve the system. So in this case, we're not so concerned about, you can use all the different techniques, LU factorization or whatever you want to do. In this case, just for plotting purposes, I'm also going to add in the boundary values, because in general, the vector wouldn't have those. So in the interior points, so I'm just adding the boundary conditions. And I want the interior points of view, not including the boundary conditions, to be what's solved for here. Okay? So we're just solving the matrix, however it's going to do it. And if I plot this, see that it worked, which is great because we kind of expect it to. I'm not even using that many points here. We can look at convergence. Convergence is going to be dependent mostly on the fact that we're using a second order scheme. So that's going to be the major thing. If I increase the number of points, it's going to increase in a second order fashion in these cases. Because we're kind of assuming that we're solving this perfectly, or at least down to machine precision. So this is basically the step where maybe you'd want to use an iterative solver or something like that. You still need to construct this entire thing. Okay. All right, so that's one way to do this. The more complicated way, I'm going to try to do this, is to use something that's called sparse storage linear algebra. It really is predicated on the idea that these matrices are by and large empty. So what we can do, there's a bunch of special techniques that allow for doing linear algebra, but with the idea that somehow this matrix has a lot of zero components. So there's all sorts of ways to store these things. It's almost more of a computer science topic. But you could think, OK, so if I have 3 diagonals that I know are non-zero, or maybe they even have zeros in them, why don't I just store those rather than the entire matrix? Right. So that's the idea. And then if we're doing matrix vector products or something like that, we can take into account the fact that there's just 3 diagonals that are non-zero. We don't need to do the entirety, because most of the values are going to be 0, and so therefore giving you 0 back out. So oftentimes in this type of problem, we try to use sparse linear algebra, sparse matrix storage, and things of that nature because of the fact that most of our matrices, even for very complicated problems, are going to be by and large zeros. And we can take advantage of that. So in NumPy, actually SciPy, I need to do another import up here. So I'll just do it here. So NumPy doesn't actually have this. It's in SciPy to do all this stuff. But we can do very similar types of things. So we can actually construct A with a slightly different command called spdiags, so sparse diags. And you can actually add multiple diagonals to this piece of this. So what we're going to do is we're actually going to, I should have probably not deleted this thing, but I'm going to reuse my diagonal. I still need that. And what I'm going to do is I'm going to say I have a list of these diagonals. I want you to put these diagonals like that. So those are my 3 diagonals, just like I had before. And actually, sparse diagonals knows better to how to cut off the pieces of it. So that's actually kind of nice. And then I say where these diagonals live. So it's another argument. And then I need to say the size of this matrix, because I'm actually constructing the entirety of the matrix. Hopefully that works. Yes, OK. So hopefully I constructed this right. I believe this still works. So you can see SPI still works, and it actually is a little bit different looking, but you can still see what it looks like. If I actually print out A in this case, it'll look different. And in fact, this is the representation it's using. So it's actually storing the coordinate, the indices of the particular non-zero value, and that's all it's keeping track of. Now, if you did this for the entire matrix, this would be silly because you'd have to store 2 more numbers. But as long as the matrix A is by and large 0, you're only storing these 2 extra numbers for those non-zero values, and then this is actually more efficient storage-wise. Okay? And there's 6 or 7 different other variations of this. You could probably come up with some of your own. But by and large, when you're actually debugging or you're trying to write something like this, it's best to not go to sparse because that's much harder to see what's going on than doing what's going on with just the regular kind of things. But at this point, that's the one command that we need to do. We do need to solve use a different command here. So I think it's spsolve. Hopefully this works. Yeah, so we just have to change this. It has to know that it's solving a sparse matrix. And we could also turn B into sparse, but vectors usually doesn't really matter for. But you can see we can actually get back out the same solution. And this is just saying, well, there's different formats for these sparse matrices, and some of them are more efficient at doing certain actions. Matrix products is better in certain formats than others, and this is just telling you you should probably use this other thing, and you can always force it to do whatever you want, but that's not too important. So that's another way to store and actually do the exact same thing. Definitely, if you can use sparse matrices, definitely do them. Just be careful that you're making sure that you're doing what you think you're doing at that point. Any questions? All right. Okay, so those were easier boundary conditions. Well, now we want to talk about not so easy boundary conditions. So Neumann boundary conditions. Who knows what a Neumann boundary condition is? Some of you very tentatively putting their hand up. We have a derivative, okay? We can have boundary conditions with derivatives. We had one over here for initial value problems. Unfortunately, now it's not so clear. We now have something that isn't representable. We know the value of it, the derivative of a value, but we don't, how do you put that in to your matrix? So I want to give you a couple of minutes to think about that because it is kind of an important point. And it leads to lots of different things. We're going to talk about a ghost cell technique. There are other ways to do this as well. But think about what would you do to actually represent a Neumann boundary condition. On one side, if it's on both sides, we have another problem. But think about that for a couple of minutes, and then I'll show you how we're going to actually solve this. Okay, so the ghost cell technique or the ghost point technique, the kind of core idea of it is that although we are going to use, we don't know UN U1 through U capital N, so these are the true unknowns, we're going to add an unknown to each end of this vector. Okay? So U0 and UN plus 1 are going to be the boundary conditions. So one of those, in this case, the example I'm using, we actually do know U0, it's equal to 3. So we're going to use that to our advantage. We don't know UN plus 1, though. Right? We know it's derivative. But we're going to formulate another formula for UN plus 1 that's going to actually equal -5. Okay? So, and we know how to do that. We know how we can formulate this as a finite difference again. We just have to be careful because we don't actually have any points to its right, but we know backward differences. So we're going to use a backward difference to approximate the first derivative of that particular point. So in terms of the matrix, we're going to put delta x squared inside of this thing now. And we know that U0 is equal to U of A. Right? That's given to us. This multiplication by the vector unknown U is just going to give us U0 is equal to 3 in our particular case. Right? So that's just stating that U0 is equal to the boundary condition. What about the bottom corner? So this is, without this row, this is the normal thing. This is going to be basically the centered difference for UN, well, actually UN, right? It's using this value, UN plus 1, so that's going to multiply, if I multiply this by a vector, this is going to be the UN plus 1 value. I don't know that again, right? I know it's derivative value at that point, but I don't know what it is. So it's going to be an unknown. We're going to solve for it. It's how we're going to solve for it, coupling it to the other one. This is a backward difference centered at UN plus 1 using UN and UN minus 1. Okay? So this is one way to incorporate Neumann boundary conditions. This is a derivative approximation, and we're going to solve for that approximation as we go. And then on the right-hand side, we know UXB because that was given to us, and so therefore that's what's on the right-hand side. It's not F anymore. So this is basically what we're looking at up there. Okay. So the nice thing about this ghost cell, ghost point technique is that you really can actually incorporate all sorts of different things into a matrix and just solve the matrix and formulate your AX equals B a little bit differently. But the one caution here is that this is no longer necessarily going to be in the right form anymore. You've now polluted your matrix with rows that are not 1, -2, 1. So you do have to be a little bit careful about that. Oftentimes, this is still going to be fine, and sometimes you can actually even get around the fact that you have different rows all of a sudden, but it's no longer necessarily guaranteed. So you just have to be careful about that. Okay, so altogether, the system looks like this. Again, we have U0 through UN plus 1. U0, we're going to force to be UA. UN plus 1, we're going to solve for. We know the derivative value of that. So we're going to do another example. I think due to time, I'm just going to code it. So we have basically the same setup. We just have to actually modify the matrix A a little bit and modify the right-hand side a little bit. So the easiest way to do that is just to say, well, I'm going to evaluate B and a little bit further. That's just actually saying B has to be have 2 extra elements into it. We're going to change those. We know that 0, 0 in our matrix is supposed to be 1, and then the other value from before that is no longer the right thing, I have to set to 0. So that's taking care of this first row up here. And then I need to handle the last row, so that's going to be -1 row. So the -1 value is going to be 3 divided by 2 times delta x. -2, so this would be the second element, second column from the ends was -4. And this last one was 1. So that's -3. So 3, -4, 1, 3, -4, and 1 for that. So just replacing that last row. I also have to modify B because I don't have F evaluated at B. That's not what I want. I actually want B0 to be U of A, because that was the boundary condition. And then I have U of X of B. So that's the boundary condition on the right-hand side, just plugging it in. And I'm going to solve this the same way. Note that you can, of course, do this with the sparse matrix business as well. It's a little bit harder because you actually do have to modify pieces of the sparse matrix, but you can do exactly the same thing. Sparse matrices can be indexed just like any other matrix. Now we can see it works, perhaps unsurprisingly. So the key is basically it's the same exact matrix, and we're just modifying the first and last rows so that it represents our boundary conditions. Okay. Any questions on that? I'm going to finish up. Okay. So we've talked a bit about this, the iterative methods and things like that. This is where those iterative methods really come into play. We can use conjugate gradient, and we can solve these things very quickly using iteration methods, often iteration methods. Conjugate gradient, for instance, is going to be faster than Gaussian elimination. There is some concern that you may, now you have a convergence of a different thing, but you can completely use it. With that, I think I'm going to skip ahead because this is mostly talked about before. You do have to be a little bit careful about these things, though, because now you do have two different ideas of convergence. And you want to make sure that if you're converging in the sense that you're making delta x smaller from your derivative versus taking a number of iterations, those are two different things, and they can interact in various ways that might not be expected. But they completely work. And by and large, actually, for PDEs and more complicated types of things, linear systems is really how we formulate these types of problems and solving them using optimization algorithms and things like that. So with that, actually, we're going to end a little early. So it's been great. This is the last time I'll be here. So up in front of you guys anyways. So if you have questions, I actually will be out of town again, but definitely post them the campus wire for the final exam. Just make sure to make it only visible to the TAs and myself. You can send email, but definitely send email to all of us as well. Campus wire is a little bit easier because then we can answer in LaTeX and programming and types of things. If you have concerns and things like that, let me know, ideally before the final exam. But other than that, it's been a pleasure, and I will see you around. Take care.